early 90s, in the early 20th century. It was used for detecting, for verifying whether or not there's a medium in vacuum. And the medium is called ether in type. Okay? Because for a long time, scientists have been suspecting that there's something in vacuum supporting the propagation of lights. And it turned out that this interferometer proved that ether does not exist. And then that led to the conclusion of the Einstein's special relativity theory. Okay? And then eventually affect the derivation of the general relativity. And that is the space and time we understood today. Okay? And this interferometer is a wavefront splitting interferometer. You can see that if you have a light coming in this direction, it's a split it into this path and come back. And it's a split it into this path and come back. And then there's an interference screen at this location. And so the wavefront is split right at the surface. But if you look at this path, well, it enters the material once, and then for this path and for this path, the path is common. But then for this path, it go up and come down. So it repeat the propagation of the ray in this material twice. Go up and come down. So this path is in this medium repeated twice. So we have to put a compensating glass right here to go through this material and back again, so that the path length, the physical path length, if the physical path length here is the same as this one, then there's no optic path difference. We have two things, okay? One is the optic path difference we define, right? We have OP20, we have path difference. Optical path difference is that you include the refracting index into the consideration, and then calculate the phase. If you look at how we define the optical path difference right here, that is there's a refracting index included in the calculation. But the actual path difference, in fact, is R1 minus R2. Okay, and what is critical in interference is the optical path difference, because this optical path difference will give you a phase difference according to this calculation. The phase difference is going to be equal to the vacuum width number multiplied with optical path difference. So this is a very important definition. If you calculate the phase, the actual propagation phase in the light, then you have to deal with the optical path difference. But to you and me in space, we care about the physical path difference. Okay, the physical path difference is that from this point to that point without considering the refracting index. All right, so for this reason, we put this slice, direct slab into the microscope interferometer right here to make the physical path difference the same, and also the optical path difference the same. If D1, D3, D4 are equal to each other, D1, D2 are equal to each other, right? If D1, D2, D3, D4 are the same, then we have to put this direct slab into the path to make the optical path difference the same along this direction and also along this direction. You understand why I'm struggling, right? Okay, for microsensor interferometer, if I have the same path length along this direction and this direction, I run into an issue that optical path difference are different. Even though this is 1 meter, this is 1 meter, the optical path difference will be different. Because the light going through this material twice, come up and go down. And for the light going this direction, without this guy, it's all in vacuum. There's no material path. So even though physically this path length equal to this path length, the optical path difference will be different. To make them the same, I have to insert a compensating glass right here with the same thickness, so that along this path, the light going through this glass once and twice. Along this path, the light will go through this glass once and twice. Therefore, with the same physical length along the two arms of the microsensor interferometer, I can have the same optical path difference. And this is important for measuring the coherent length of a light source. And in a moment, we'll be talking about it. Okay. So with this compensating glass, the analysis becomes simple because the paths along this direction coming down and along this direction coming down are exactly the same. Because I have beam going through this material twice. I have beam going through this compensating glass twice. Okay, so this is the reason that we put this phase compensating glass here. All right, so now we need to be careful about additional phase accumulated from this reflection. There's an external reflection at this point, and then there's an internal reflection at this point. So the optical path difference are the same with this compensating glass, but optical phase difference would have additional pi phase shift here. Okay, because for external reflection, you have this formula. Remember that you have this formula at normal instance. So now we sort of simplify this with like the normal instance kind of formula, so that you can quickly get the idea that if you have an external reflection, this means N2 larger than N1, right? The second material has a larger reflecting index. If N2 larger than N1, then you have a pi phase shift upon reflection. But for this one, it's internal reflection. This is the reflection surface. Internal reflection, there's no additional phase shift associated with it. Okay, so you need to take into account that along this path and along this path, there's an additional pi phase shift accumulated through the propagation of the light. And then if you do it, take into account this pi into this phase difference calculation, then you end up having this result. And for microsensor interferometer, D1, D2 are the same, D3, D4 are the same. Okay, the reason we keep D1, D2, D3, D4 is because we have the last page. We have D1, D2, D3, D4. Okay, and then for Magenta interferometer, you have D1, D2, D3, D4, and for example, the Magenta interferometer, D1, D2 are not necessarily the same. Okay, and D3, D4 are not necessarily the same. But for microsensor interferometer, D1, D2 are the same. D3, D4 are the same. Okay, so this is the difference. All right. So once you take into account the reflection phase, then you have an optical phase difference that determines the interference fringes right at this location. Okay, so basically you'll be calculating the path difference, and then additionally you have pi right here. Okay, microsensor interferometer again has been very, very useful in the scientific advance. And in the moment we're going to use it for the coherent length measurement. And then I'm hoping to give you one experiment to do, okay? All right, so think about that this is a microsensor interferometer, and there's an arm going in the vertical direction, the other arm going in the horizontal direction. If I just expand it, this is a screen. If I just expand it, then it's going to be like this. In your textbook, you have a screen right here, and then this lens is going to focus the plane wave into a viewable screen that gives you the fringes. Okay. Whenever we talk about interference, we always use plane wave. How do you view a plane wave? If I have a plane wave like this, then the way to see this plane wave is to use a lens to focus it to the focal plane. This is how you see the plane wave. So intuitively, this is easy, right? Right? This is how you view a plane wave. All right. Now, if you have a plane wave going with an angle, then you're going to focus this plane wave onto a point like this, also on the focal plane. Well, this is a little bit over, but anyway, this is how you see a plane wave. Even though this plane wave propagates with an angle, then you still see the bright spot on the focal plane. So this is how you see the plane wave, right? So when we talk about interference between plane waves, then we use the lens to see the spot on the focal plane. So imagine that you have a source right here. You have a source right here. Okay, you have a source right here. And then you have a light ray representing the plane wave going in this direction. And then you have mirror 1 and mirror 2. This light ray will go to mirror 1 and mirror 2. This light ray will go to mirror 1. This light ray will go to mirror 2. Right? So you can see the corresponding location of M1 and M2. And for example, the mirror 2 is going to reflect this light ray along this direction. So mirror 2 will reflect the light ray along this direction. And then for mirror 2, for this mirror, it's going to reflect the light along this direction, going down along this direction. And these two rays will interfere with each other. Okay, so everybody can catch this configuration. Start with ruler. Could you understand this? So think about you have a light ray going in this direction and bounce along this vertical direction and come down to this screen. And then this beam splitter is going to split and then light ray along this direction, and this mirror will reflect it back to this screen. And then you see interference. Okay. So if you just expand it, this is the source. So suppose you have a source generating a light ray to hit this M2, it's going to refract to hit this M2, and then it's going to refract it back, right? To hit this M2, and then it's going to be refracted back over the screen. And then this light ray is split into the second pass to hit M1 right here, going up, and then come back to this screen. So this continue to this point and come back to this screen. But then you use the lens to focus it to the screen to see it. Okay. All right. But then the light ray coming down from this, well, this is a mirror. So there's an image. There's an image generated by this mirror So the image of this screen associated with this mirror is going to be at this location. Okay. So the image of this mirror relative to, well, the image of this screen relative to this mirror is going to be at this location. Okay. This is mirror, just a flat mirror, right? So whatever you put in front of this mirror is going to be imaged in the back. And then, same thing for this M1 is also generate an image of this sigma screen right at this location. So the path difference, initially if you have the M1, M2, the path difference is D, for example. But then, eventually when you reflect it back, the path difference is twice, become twice. Well, if this is too complicated for you, just look at this. Initially, if I have the same path difference, then you have interference fringes. And then if I just move this by a small distance, the difference is amplified by a factor 2, because the path will go this direction and come back, right? So initially, if I have a mean separation of D, now my mean separation is going to be 2D. Okay, if you don't like this, too complicated, then just look at this. If you move a small distance, say 1 centimeter, the path difference between these two will be 2 centimeters, because you go this direction and come back. Okay, so it sort of double the path difference. But then if you propagate the light, the ray with some angle, well, you have to take into account this angle. So the actual optical path difference is going to be 2D cosine theta. Okay, this is 2D, this is the propagation angle theta, and this path is 2D cosine theta. All right, you simply have to go through the derivations by yourself. But I sort of walk you through this calculation so that it will be easier for you to see it. All right. So, but then you have to add a pi phase shift here because you have a external reflection at this point for the light coming back from the M2. So you add a pi phase shift here. Now, once you have the optical phase shift, then you can start to count the fringes, right? Because when you have a contracted interference, and you set this optical phase difference to be integer multiple of 2 pi, so you have constructed interference. So you can start to count the fringes at this angle. And then you see, okay, you have the bright fringe here, bright fringe here, bright fringe here, bright fringe here. This is the actual experiment I did some years ago. So I did not copy this from any place. I did this experiment myself and took a photo myself. Okay, and so you see off-axis interference fringes because of this theta effect. So you can count those fringes. Well, in the moment we're going to see why with a large angle the change of fringes become fast. Okay, but then you can also count the dark fringes. You can count the dark fringes. When this is equal to integer mod of 2 pi, then you have dark fringes because you have the additional pi phase difference upon this external reflection. Okay. All right. So this is how you count the fringes. But it's interesting enough. If you set d equal to 0, this means that there's no path difference between this and this. When d is equal to 0, what happens? Well, you have dark fringes at the center. For microscope interferometer, if you don't have any physical path difference between this arm and this arm, you always see a dark fringe right at the center. Okay, so this is a beautiful fringes you can see from a microscope interferometer. All right. Given this, we can continue to understand one application. Well, why the light why the light can interfere with each other. Okay, we have, for example, Young's two-slit interference. Previously we have this. Well, you have Young's two-slit interference. One light source here, the other light source here, and then you see this up and down as a wave. And then you have interference here. Well, I think we cannot take for granted that you will always see something here, unless you pre-draw this up and down on this page. Well, whenever you write down, whenever you draw something up and down, this means that the phase is very predictable. You can predict the phase so that you can draw this up and down, right? And same thing, if you can predict the phase of this optical wave, then you can do interference. If you cannot draw this up and down phase, then in fact you see nothing at this location. So, for example, if I have kind of random kind of wave mixed with a lot of frequencies, and then you try to overlap them. For example, if you overlap this with this, would you be able to have interference fringes? No, not possible. You don't have any you don't have the stationary constructive interference or destructive interference. So you are not going to get any interference fringes. But if I have interference, if I have a light source like this, well, in fact, this light source is just like this. Interesting enough, what you see from this room, the light source just like this. But if I just use this to split it into, well, semi-through a beam splitter, and then bounce this along this direction, and bounce this along this direction, and come back, and come back. In fact, if I don't have any path difference, between these two arms, I will be overlapping the two same weight together. I can duplicate this along this arm, and duplicate this arm, along this arm, and come back and overlap them. Agree? You look confused. I'm sure you understand this, right? If I have a beam splitter like this, and then if you have something on coin, and then you split this one coin along this direction and along this direction, and then you have a refractor, and come back along this direction, and come back along this direction, and then you will have two coins that look exactly the same. And you can overlap them together. Agree? Right, I can duplicate this one by using this beam splitter, doing like this. Right, so if I have a garbage like this, then I can create this challenge. I can create a garbage here and also another garbage here. They are exactly the same. And then if I just send them back and then try to overlap them, can they be overlapped well? Of course, yes. So I see something here. But if I have any optical path difference between this and this, you'll be overlap this, with if I have an optic path difference, you'll be overlapping this with this. You cannot really add, you cannot really get the constructed interference. For example, this part overlap with this one. So you don't quite get the maximum interference, right? So what is worse is that if you increase the delay, if this is delay away from this this pattern, you don't generate interference fringes anymore. Okay, so this is the setup. This is a setup. If you do a translation along this direction, relative to this one, this is the setup to see how good this wave can produce interference fringes. Okay, can you more or less understand this? If you want to have a interference, then basically this phase and the phase variation and this one has to be more or less the same. Well, I cannot do the interference, but I can do this, right? I've got some here, I have some here, then when I overlap them, they generate a constructed interference. And then when I move a little bit, they generate a little bit. When I move a little even further, they generate less. And then when I move them away from each other, I produce no interference fringes. Agree? All right. So we say that the length of this wave is a coherent length of the source. Because within this length, I can produce interference. You can take this, right? If I want to produce interference, somehow I need to overlap them, and then this phase has to be the same as this one, so that I can do interference. So I have constructed interference, I have destructive interference, constructed interference, and partial destructive interference, and partial constructed interference. And then when they separate from each other, then you don't have interference. Then we say that, hey, this length is a coherent length of this light source. Okay. Everybody agree? Li Xiaolong? Okay. All right. So let's use microscope interferometer to measure the coherent length of a light source. Okay. So suppose that I have a light source that the phase within this time is predictable. Okay. For this light, you see it's a continuous wave, but the phase could be only predictable within a very small fraction of time. Okay. In space, I can just multiply this with the propagation speed of light in space to get certain length. We call this coherent length. So coherent length is a distance in which the optical phase is predictable. Okay, and practically is a length separation between these two arms, within which you will see interference fringes here. Okay, and by Fourier transform, you also understood this time and spectrum are conjugate variables. With a certain width in time, you can also calculate a certain spectral width in frequency. And if you multiply these two together, you get a value approximately equal to 1, not quite equal to 1, depending on the spatial distribution or the temporal distribution of the wave. So this is how we measure the coherent length. Okay, you move this arm from the 0 position and then push a little bit D, and you can still see fringes. And then if we push it too much, then you don't see fringes here, and then you understand the maximum length. That gives you interference fringes, and then this gives you the coherent length. And then from this coherent length, the spatial length, you can deduce a temporal coherent length. And then from this temporal coherent length, you can deduce the spatial line width of your light source. Okay, so this is how you define the coherence of a light source, or the temporal coherence of a light source. For a laser wave, the coherent length can be very long, because if you look at this Youngster slit interferometer, wow, this coherent length is very long, and it is written as the sinusoidal oscillation over long distance. Okay. But for this light source, the coherence, the spatial coherence, the temporal coherence is very poor, very poor. Okay, because the spatial line width is very broad. If you look at this, if I have a big delta F, this means that in space is very short distance. Okay, Lisa, you got it right? For very broad broadband light source like white light, it contains a lot of colors. So the first exam question for your midterm exam is to let you calculate the wavelength of the white light. You have blue light, green light, yellow light, red light, and so on, right? And so if I have a very broadband source like this, then the coherent length is very short. And then I'm sure that I will either give you homework problem or the midterm exam problem to calculate the coherent length of this white light source. You know how to do the calculation. For example, if you have a Hin-Yin laser, it's a laser. The spatial line, the frequency line width is for 3 GHz. Okay, then we can do the calculation for 3 GHz. We have delta F equal to 3 GHz. Then from the Fourier relationship, your temporal coherent length is going to be roughly 3 GHz. This is about 3.3 nanosecond. Right? And then the coherent length, the coherent length is about the, what did I do? COH. It's about the speed of light multiplied with delta t. This is about 10 centimeter. This is the speed of light. So this is why I say that hey, it's about 10 centimeter. So if you change to D, if you move this within 5 centimeter, you see interference fringes. Because if I translate this 5 centimeter, the path difference between these two will be 2 times. Okay, any question about this? So this is how you measure the coherent length. Well, in a moment, I'm going to give you one experiment, but not right now. I want to move down, but everybody understand this. Sure, no problem at all, right? So it's understood to you. So in a moment, we're going to split this white line into two beams and then overlap them to do the interference. Okay, but before we do that, just try to understand why the fringes become varies fast when you get to a large angle. Okay. Again, this is a drawing that I try to do it here. If you have an off-axis plane wave going to a lens, you have an off-axis point on this focal plane. So that's how you form this interference fringes on the focal plane of a lens. Okay. All right. So if we count the fringes, when you have a small angle, theta 1, then with a non-zero d, you have this result. Well, when you have the theta is equal to 0 right here, when you have a theta equal to 0, then 2d equal to m0 lambda 0. This m0 is the order number. Okay. Basically, you'll be counting the path difference in terms of the number of wavelengths in your interference. Okay. You can just set this theta 1 to be 0, so this 2d is equal to m0 lambda 0. But then if we increase this angle, then this m0 is start to decrease. Okay, and then so you can imagine that the dark fringes is the location of the dark fringes at theta 1, theta 2, and theta p. Okay, we pick up the dark fringes for calculation. Remember that we have this dark fringe right here. Okay, we have this dark fringe. We set this initially to be 0. That is right at this location, and then start to increase theta. Okay, start to increase theta, and then you can calculate the piece fringe, by picking up this formula and this formula. Okay, just solve this m0 from this formula, and then put it into this expression, and then do a small angle expansion, Taylor expansion of cosine. It will be 1 minus the square of theta divided by 2. Okay, and with this, you start to focus on the angle where you see dark fringes. Right? So you calculate this theta p as a function of p. So you see that when this angle becomes larger and larger, then p move really fast. Okay. So p changes rapidly with the increase of theta because p is proportional to the square of this theta. And that is why you see this of axis fringes, they change very fast. But near the center, the fringe change quite smoothly. And another thing is that if I have large d, the path separation, the separation of paths between these two, if they are big, okay, and the change can be fast. Okay. If you go to this, when this d is big, when d is big, a little bit change of the theta p will give you a fringe. Okay, so if you separate the two arms to a large distance, then you see the density of the fringes become big. And again, I did this experiment by myself, and I took all those photos. It's a fun experiment. Okay. And if you have misalignment of the two beams, then you see that the interference fringes become asymmetric. Okay. So if you have the misalignment on beams, and then you primarily see off-axis interferences like this. It's a beautiful experiment. All right. Any question? I'm hoping that I don't just give you formulas. You can also see some beautiful photos. Okay. All right. Now, I want to talk about fringes of equal inclination. Okay. When we say equal inclination, this means that the plane wave is incident on some thin film, and the reflected light will form interference along some direction. Okay, so we'll fix the direction and try to analyze the path difference. Well, for this case, you have a light source right here, going along this direction with the incident angle theta I, and then you transmit this film. This is a film with a thickness of d, and then come back, and then you have the first refraction here, second refraction here, and then you try to analyze the phase difference between this one and this one. All right. And the internal angle, the internal refraction angle coming down right here is this theta t. Okay, this one and this one. So the path difference between these two, if we look at this, the path difference between these two is that the first path will come along this direction and have an additional path difference here, and then the second path go inside, come down and come back again. So there's a path difference right here for the second beam. For A, B, B, C is right here. It's a reflecting that's NF. Okay, and for this path is AD, reflecting that's N1 outside this beam. So we write down the optical path difference. And optical path difference is very important in your calculation. Once you have it, you know the optical phase difference by multiplying this with the K0. Okay, remember that you have this. You have optical path difference. You multiply with a vacuum wave number, you get the interference phase. But then be careful. You have additional, this is the external refraction, this is the internal refraction. So you need to, sometimes you need to add one pi phase shift into this equation. Okay. All right. The rest will be just trigonometry calculations. So this page gives you step-by-step instruction for calculating this optical path difference to a very simple compact formula right here. Okay, QNFD cosine theta t. Theta t is the angle inside this film. Okay, so all those things just try to help you to get this very simple and compact formula for the optical path difference. Okay, so go through this derivation by yourself, step by step. You come down to this very simple result. And then there's an external refraction, there's an internal refraction. Then we have to add pi. We have to add pi to this optical phase difference. Okay. So the calculation steps are quite simple and straightforward. But details you need to write by yourself. Go through the steps on the page. Okay. Once you have the optical path difference, then you can count the fringes. Okay. And this is also a photo I from my experiment. I just put some oil on water and take a photo. So this is also my experiment. And so if you have some oil on water, you spray out. You saw it before, right? I heard that last week it rained quite hard. And then if you walk on the street, you see some water with some oil on it. And that is from the automobiles. And you can see this interference fringes. Okay. So once you have the optical phase difference, then you can count the fringes. You can count the fringes when this optical phase difference is the integer multiple 2 pi. Then this is the optical path difference. Is the integer number of wavelengths plus half wavelengths. Okay, for the bright fringes. The reason for this additional half wavelengths is because there's a pi phase shift right here. from the internal and external reflection. Okay. And so this becomes the standard calculation that if you want to count the minimal fringes, then you set this phase difference to be integer multiple of pi. Okay, and then you can determine the fringes angle, but be careful that the theta d is the angle inside this field. It's not quite the angle you saw outside. Okay, but this is a very compact expression. We all want to use it. Right, so this is how you calculate the interference fringes from the same field. All right, then let's go back to this Michelson interferometer. Well, for this Michelson interferometer, the path difference is the length between these two arms. And then we can use the path difference and then the interference fringes to determine the coherent length. All right, you can also use this to see interference fringes. And then when you see interference fringes, well, we can also say that the thickness here, 2d cosine theta t, that theta t to be almost 1. This must be within the coherent length of this light source. Otherwise, I will not be able to see these fringes. Agree? Right? For Michelson interferometer, if I move this too much, and this is a broadband light source, then I cannot see interference fringes. Well, same thing, if this too thick, if this D is too big, I won't be able to see the interference fringes. Agree? We have some experiment for you. Oh, we'll do it after 10 minutes. Okay, so we're going to have a fun experiment after 10 minutes. And then